Okay, so we're live now on YouTube. Today, as I promised, we were going back to to EGSnrc. On the channel, there were a few questions from new subscribers, and I invited them to join the session. So maybe we'll just wait. So what we're going to do today, actually, all of you uh, have the files. Singh asked that we should go back and talk about latches uh, on the channel. Uh, One subscriber had problems uh, running the demo linac that's available with the EGS. So I thought, so my voice is clear. Can you hear me? I guess. Okay. So all of you have installed EGS properly. There is actually EGS comes with two actually examples for Linux. So if you go into your Beam NRC data, Beam NRC spec modules, you should have a Linux called EX. So this is example 10 MEVE module and EX16 MBP. You could also open Beam. So Beam, where is this? So we could open Beam, and we can load that Linux or accelerator. We just hit on load, and we're going to do the photos, 16 MB photos. The text data file that's used to for this Linux is the 700 ICR. You will find it not in your local area, but in Henhouse. So if you go and browse Henhouse, the data is 700 ICR. This Linux is a very standard Linux. It's made out of component modules, slabs, that represents a target, cones, 3R, the primary collimator, flattening filter, a chamber, mirror, jaws, and slabs. So this is an old example. It does not have MLCs. So it's an old example that we are going to, since all of you have that Linux. So the next step, what do we need next? We need an input file. Of course, when you load the Linux, there is nothing on these components. So an input file will have data for example, what's the source, is the particle, and some information about the component modules, the geometry, the materials. That's all in the input file. There is actually an input file, an example input file, and I'm going to show you where that is. So we have, if you go and do tilde, you put dollar and it's Henhouse. Okay, that should take you to your Henhouse area. And inside it, there is a directory called Omega. Okay, and then there is a beam NRC. You look there. Then we have beam NRC examples. This is the directory that I'm looking for. So CD beam NRC examples. If we go inside, you will find actually those 4 examples for beam NRC, but we're interested in the one with the photos. So we'll go into 16 MB. And inside there, you will find this is the module, spec module for the linac. It even has a sample EGS face-based file. But the file that we're interested in is this one, the EGS input. We need to copy that file into the directory where we have the example linac. So from here, so beam NRC, we have loaded the linac. Probably it's a good time now to compile it. I have it compiled, but maybe some of you don't have it compiled. So you just hit on compile and then build and compile. It should do, you should see this stuff. So it should compile the linac. And we should have now a directory under our home area. So let's go and I'll show you. So X home. So we should have this directory here. Okay, so it should create, when you build and compile, you should get this directory, this folder. The next step is you copy the input file that I showed you. Okay, you copy it into this folder. I have done it and it is here. Okay, but if not, just copy it from the directory I showed you under the henhouse / omega / beam NRC, and then I think there is / beam NRC examples, and then you will find the linac. So try to copy that input file into this directory. So I've copied it, and now this has compiled. And the next step is we will open the input file. Okay. So we will go inside the directory, and there it is. That's the input file. When you load it, now the data for the linac for that geometry, everything now is filled or captured from the input file. So we'll have, for example, the target thickness, all of this there. So the information, we have the input file ready. We can review now the linac. So we hit preview, then here you have target, you have this is your primary collimator. And here, as I can see, it's made out of, I think, iron, not tungsten or lead. So it's made out of iron. Then we have here the flattening filter. This is the chamber. I think we have the mirror. I can see mirror like this. These are the jaws. And then we have air, and the last slab, it finishes at 100. So obviously, with this input file, we can, it's made so that we can generate face-based files at 100. Is everyone clear? Should I repeat anything? Okay, stop me if there is something not clear. If you cannot do something, I prefer that we pause and help you to do that stuff. Okay. Okay. So the next step, we have the input file, and then so the next step is probably we're going to run now. I see everything runs properly, so it's running. The input file, I think it simulates 1500 histories. And at the end, in the phase space file, we have how many we got. So at the phase space file, it's not written here, but usually sometimes we have a number of particles. Okay, so anyway, we will probably have some particles in the phase space file. Now we want to actually run, if you have a parallel processing, that's excellent. So I'm going to increase the number of histories. So instead of 15, actually it's 15,000 here. So we'll just put, okay, we'll do 1 million. And I'm going to save now, input file. And I'm going to run it, but I'm going to do it in parallel. 8 cores, so we're going to execute. So if submission is okay, then okay, it did not go because I should see now my CPUs running. The best thing is that to go through, I'm going to do it through from the command line so that I see what's happening. Okay, so EX and then linac name, then the input file, and then 700 ICRU. Okay, so it runs, no problems. Now we're going to use, and I think Beam has the problem submitting to the batch. So EXB, and then at the end, I'm going to put P equals to 8. When I do this, you can see here on the right that, okay, my CPUs now are running. And we can look at the log file. And we will just monitor the progress of the log file as we'll see how long this is going to take. Okay. So I hope now this demo accelerator, everyone can actually run without any problems. Okay, any questions before we move to the next step? Okay. So the next step is we want to look at latches. This is what, so now when I look at the progress of the log file, I'm around 20%. So 200,000 histories was simulated, remain 700. So 100,000 histories are being actually simulated this time. Okay, so the next step is we're going to look at latches. This is what Singh actually asked in the group, the class. So we're going to look at, and the idea behind latches is you can know the history of particles that reach your text plane. So for example, when we do this simulation, we're going to collect particles at 100 centimeters. It might be desirable for whatever research you're trying to do is to know, for example, okay, did this particle that reached there, did it actually come from, did it interact in the jaws, or did it actually come to the center? So this is one example. You might want to know if the particle, for example, was scattered from the final collimator or not. I mean, you decide what sort of history you want to know about the particle. So we can use latches, and to do that, we will open the, so let's look at the input file. Where is it? Okay, I'm missing here the linac, so let's close it and open it again. And we'll load the linac. Okay, and then has 700 ISO. Okay, so to use latches, we need to go and edit the main input parameters. We need to, let's say, turn latches on. That's the first step. So here, in this input file, actually latches, they are actually turned on. They are set by interaction. What does this mean? It means that I think there is a 32-bit, or I forgot how many bits, 16 or 30, attached to each particle that reaches the phase space file or reaches 100. And we can associate one of these bits with with a certain component in the linear accelerator. So for example, suppose I want to associate, I want to know if the particle has interacted with, let's say, the X1 jaw, okay, the jaw, X jaw on the left. Then, so now we have it here turned on, we have it set by interaction. So now when we go into the jaws, and these are the two pairs, I have here associate with latch bit. It's already actually, with this example, with the default example, they do actually have latches turned on. So bit number 10, when you see a particle with bit number 10 is turned on, you know that that particle in its history, it has actually interacted or came from an interaction from the X jaw. So here we have X jaw, it's not X1 and X2, it's just both the pair, the X jaw. And if bit 11 was turned on, then we know that the particle has interacted in the Y jaw. It's possible that the particle for some reason could have interacted in the X jaw and in the Y jaw. So then in the latches, you're going to see for that particle, bit number 10 is turned on and bit number 11 is also turned on. Okay. So let's see if, since this has latches already turned on, let's see if, okay. So now the simulation finished. Actually, it's obvious from the CPU here, on the right, nothing is running. The next step is we're going to add the phase space file, since I used parallel processing, add phase space file, and then we'll put the input file name. And this is the desired output file name. I usually keep the output file the same as the input file. So the extensions are going to be here. It's going to be .x EGSnrc 1. And then I did the parallel processing for 8. And the first one is number 1. And the last one, I think it's phase space number. In a simulation, you are allowed to acquire phase space file, 3 phase space files at different levels. So if one wants, for whatever reason, they can, for example, let's compute accelerator. If you want, you can actually acquire a phase space file, let's say above the chamber, another one above the column of the jaws, and the third one is at 100. You define these through here. Now the number of scoring planes, we have only one, but I could select up to three. And then for each one, I will say, okay, the first one, I want it to be acquired after component module number 2. And the second one after component module number 4, for example. So for one, so here, since we have how many component modules? We have 1, 2, 3, 4, 5, 6, 7. So if I go and look at the data for one, it has to be the scoring plane is after component module number 7. Okay. So if you decided to actually have 3 phase space files, then the first one will have at the end of the extension, it will be 1, the second one is 2, and the third one is 3. So here, this is what I'm defining. I'm defining, okay, I want the phase space file number 1. So when we do this, I'm going to override whatever is existing there, and the simulation finished. Okay. In this phase space file, we have about 230,000 particles, 151,000 particles of in the phase space file are photons. The rest are electrons or positrons. Could be we could have positrons because here the energy is 16, so it's possible. And those particles, they were generated from, there seems to be something missing because we should get 1,000 here. I should have, sorry, 1 million. But for some reason, I don't know why, one of the phase space files or one of the simulations did not go that time. So these are the number of incident particles from the source. Okay. Now, to examine what's there in the phase space file, to analyze the phase space file, we need another application, and that is beam. So let's close. I'm going to close the beam application. This is beam. And there are many things that, for example, I can derive X, Y scatter plot. This shows me, it produces a plot of particles. So imagine yourself looking at, you're at the source and you're looking down to the phase space file and plotting locations of particles that reach. So we're going to put minus 100, 100. So this is the area I wanted to scan for particles, and I can decide I want you to only plot, for example, particles with energy above 10 MeV if I want. In this case, I'm just going to ask you just to look at all the particles that, so I can put 20, even higher than latch. I'm not going to choose latches for the time being, and let's go and open the file, the phase space file. So it's this one. Okay. And when I open it, it gives me the chance to save the data. I'm going to call test and maximum number of particles to plot. I know in the phase space file I have 230,000 particles. I want the software to plot all of them, or maybe just to plot the first 10,000. So let's try with the first 10,000. Okay, and then we hit on execute, and it will open. If you're doing this with Linux, it should open immediately the Grace. So this is a plot of the particles. where they are, and so on. You see here in the center, it's very dense. This is probably where we have the field opening. The field is probably, I'm not sure, we can go and look this in the field size. But frankly, I use this application just to make sure my geometry looks okay, field size openings are fine, and so on. But other than that, one has to be careful because each dot here representing a particle, uh, it doesn't take the weight, for example, into account. So it's possible, although I don't think this is in this case, in this scenario, that the particles, that a lot of particles here, they do have a very small statistical weight, whereas the particles here, they have a large statistical weight. So one would expect, if you don't just take the statistical weight into account, that any dose coming from, regions below this region should be higher than here. But in fact, no. But so this plot does not give you indication of statistical of the statistical weight of the particles. So be careful about this. Now, suppose I want to use the latches. So I want to know which particles of those 10,000 actually interacted in the extra. So we're going to use the latches. And just to show you the latch information, I'm going to go back and I'm going to list the parameters of the particles. Okay. So 100 particle type, execute. Okay. This is the list of the first 100 particles that are in the phase space file. Some information, but the maximum kinetic energy, and then for the particles, this is the energy of the first particle, 5.2. By the way, the energy is total energy. Okay, so for electrons and positrons, to know the kinetic energy, you have to subtract 0.511. And for photons, of course, the mass is 0, so this is going to equal to the photon energy. So in this case, this is actually an electron. The IQ is the charge of the particle. This is an electron. The first particle reaching the phase space file was an electron. It has a total energy of 5.2. X, Y, this is the location of the particle in the phase space file. Of course, the Z coordinate is 100 because that's where the phase space file is. And then we have the direction of the particle. So we have, these are the cosine, I think, I'm not sure, cosines or sines of the angle in the X and Y, Z directions. Okay, so usually, always U squared plus V squared plus W squared is always going to equal to 1. Okay. Z last, probably this is the last Z coordinate where this particle interacted. This is the statistical weight. And you can see this particle has a very small statistical weight. And now this is the important part. These are the latches. These are the bits. So I'm not sure in terms of because we need to know where is bit 10 and 11. Does it start from here or does it start from there? I'm not sure about that. Okay, it's not really important. As long as important thing is I know that's bit 10 and 11. But here, for example, there is a latch. So we have one of the bits. Probably this is bit 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I don't know where is bit 10 or. So it turned that latch 1. That means it satisfied the condition that it interacted in the X drop. Because we chosen 10 latch bit 10 to represent interaction in the X drop. Doesn't matter. I can use a bit 8. It's just important thing is I know which bit is associated with which component. Okay, so these are the list of the 100 particles. The nice thing about this view is that at least now we see the bits. See there is a 1, 0, and 1 and so on. So now let's go back and let's derive x bar. Okay, and I'm going to use the first. Let's choose all the particles. It's okay. But now I'm going to actually, I want to include latches. So inclusive, so filters. These are the bits. So which particles I'm interested to plot? I'm interested to plot particles that interacted in the X jar. That means I have to turn bit 10 on. Okay, and then when I hit done, execute. Okay, and override. It took longer time because now it's analyzing 200,000 particles. Okay, so these are the particles that reach the phase space 5 that somewhere, in their history, they interacted, or their parents interacted in the jaws. Okay, so this is for the extra. We can go and change another filter. So for example, I want the particles that only interacted in the X jaws. So I'm going to use 10 inclusive and bit 11 exclusive. So this means that if the particle had bit 11 turned on, don't plot it. Okay. So bit 10 has to be on, bit 11 has to be off. Those are the particles that I'm interested to plot. And the first time I ran this, my condition was bit 10 is on. But now I'm asking bit 10 is on, bit 10, bit 11 is off. Okay, so override. So these are the particles with including bit 10 inclusive and exclusive of bit 11. We can, I can exclusive of both. This is basically all particles, that did not actually interact in the X or Y zone. Okay, any questions before we move to another topic? Singh, is this clear to you?
Yeah, but I have some questions like how do we quantify that? How much contribution of the entire phase space is contributing only the X jaws or Y jaws?
You mean contribution? You could, for example, I don't know if we have an option here to count, but so you want to see, for example, how many particles have that latch, right?
Yes, yes.
Okay, okay. There are a few things you could do. Is you could, for example, let's try to derive the energy, the spectral distribution. Okay, let's see if this will work or not, because I want to know the number of particles. This is inclusive, exclusive. Okay, fine. Graphite points and fluence, let's say, is okay. So something is not. But the number is not important. Again, you seem to be, addicted to number of particles. What's really important is their weight, because you could have 1,000 particles that have a very small statistical weight, in the phase space file, and you have one particle that has high statistical weight that over contributes more to the dose, more to the fluence than these 1,000 particles. So the number itself is not really important.
So then how do we quantify that, how much contribution coming from the primary photons or the scattered photons?
When you do dose XYZ, you can actually list the dose components that you want. So I'm going to show you that. But this is, let's look at the fluence. Okay, we're doing, this is number of equal energy bins, 200, 0, and here 20. This the latch, and the term is undefined. Okay. So here we're going to use photons. Execute. Okay, let's see here. Did it actually look at the, okay, no, nothing here about the number of particles used or satisfy that condition. Okay. But the reason is because the number itself is not really important. And that's why the XY, this XY plot also is not really an important figure. It just shows you, roughly where the field is and so on. But you cannot get from it any statistically valid information. Okay. So here, for example, these are the particles. These are the fluence of or the spectrum of photons produced from or scattered or interacting in jaws in X jaws and not in the Y jaws. See, these are the energies of photons, and we know this is a 16 MeV, okay, electrons. So the spectrum, we should have a 16 MeV spectrum. We should get photons all the way here. But if I look at just the spectrum of the photons, energy spectrum of photons interact or scattered from the jaws, we have this part. So if I go back and I say none here and execute this again, okay. So you see the photon, I should have up to 16 MeV photons in the spectrum. So this is the spectrum of all particles reaching the phase space value. You could also, I mean, sometimes you're not interested you might also be interested on spectrum of photons, let's say within the open field area. Let's assume this is a 10 by 10. So I'm going to put here minus 10 and 10. I'm not sure what's the field size for this example, but you can just get a spectrum within that open area. So you know what is this here, this peak? Anyone knows what's this peak? Why do we have a peak here? Or is it an error? So why do you think in the spectrum we have a peak here? This is just, this is at 0.511 MeV. So why do you think we have a peak here? Or is it an error? So whatever spectrum produced by EGS, you believe, you will not question. Let's look at positrons. So there is a spectrum of positrons. Obviously, there are positrons being produced in the linac because we have photons with energy greater than 1 MeV. And when they interact in components in the linac, in the air, it is possible, although not really, probability is lower than other interactions, but it's possible that they will interact through their production. And with their production, we're going to have positrons. So some of these positrons might have sufficient energy to reach 100 centimeter in the phase space 5, and that's why we're getting these positrons. Some of them might annihilate, and when they annihilate, after they lose their energy, we know they're going to produce 2 annihilation photons with 0.511 MeV, and one of those annihilation photons can reach the phase space 5, and that's why this explains why we get a peak. So look at photons again. Okay, so this is the peak at 511, and that's produced by annihilation photon. Okay. Okay. In those XYZ, I'm going to open it, but not now. I'm going to open it, and I'm going to show you that you can actually now record doses in regions with latches. So for example, if we want to know, let's say the dose at Dmax, what is the dose to Dmax produced by, or the contribution, let's say, of dose at Dmax produced by photons scattered from JAWS. So we can actually get the dose from all particles, but also record the dose from particles that have latch 11 or 10. And then we can estimate the contribution. Okay? Whether that is relevant or not, that is not, that the researcher has to define, is this important for what he wants to research or not? Okay, but it's possible. Okay, so another thing I wanted to show you is with the input file again, is maybe for some reason you actually want to record the dose in a certain region in your linac. So try to, all of you, if you have EGS installed on your computer, you could just run this demo linac and it should work. Okay, so for example, we have the linac. Probably an interesting region where we want to record the dose would be in chamber here. Because the NU, the linac, the way a linac defines the monitor unit that we treat patients with is actually those recorded in the monitor chamber. It's not the current of the beam. This is why we were having this debate with Andrew on MMCTP, because now we want to actually, so when we obviously, when you have different jaw settings, uh, there is an output factor that plays a role in the monitor units calculated by the treatment time system. And especially with MMCTP, it does not record the three doses in the chamber. So he had this formula or factor of 1.02% backstack factor. This some researchers they have done that work, but he has the option of actually calculating output table, and I'm at that stage now. But anyway, suppose we want to score the dose in this region. Then that's in the chamber. Okay, the chamber has layers that look like this. And what we can do now is we can go to the central part and okay, you see this is they have associated this with latch bit 6. So that's another latch bit, and it's always good that you record down region and the associated latch bit. We could use 10. I mean, we could use 10 here also. But then the problem when I want to analyze the data, I don't know a particle with latch 10. Was it because it interacted in the chamber wall or because it interacted with the jaws? That's why use two different latches. We could use 10 for both jaws. If I'm not interested to distinguish between the X and Y jaw, that's fine. But here, this is the dose zone. This is what 0 means don't record any doses. Okay. But we can actually, so here, yes, they do actually in these layers, they have a dose zone of 5. Okay, let's look at the other layer. Okay, 6 and 7. Okay. 6. So they have some pattern where they're recording the dose into these regions. I'm not sure what these regions represent, but they have selected their regions of interest and associated with them in those zones. So after you run the simulation, then we can actually know the dose in these dose. So we're going to go to the folder and the information about the simulation is in the X list, EGS list. Okay. File. So if you open that file, it has information about the simulation, what has been done, okay, and materials. Okay, this is okay. 7 component modules. These are the component modules. And I think now it has listing the geometry of these component modules. So component module 6 is because 7 is okay. And now we have particles. Okay, these are those results. We have a table, those results. So there are different dose zones, and here we have the mass, the dose, and the energy deposit. I'm seeing this is always 0. Does that mean we don't have enough particles there? Those component one, because I think there should be some dose recorded, unless the number of histories is not enough for that, because it's air and but somehow it should be somewhere. It should be listed, and that information should be in the list. Obviously, these are the zones, but okay, these are the masses. I'm expecting I should see some dose there for energy positive. I don't know why it's not there. So unless we go and look at the input file again, uh, but I don't see it. Actually, I see it here. Okay, I think I know what is the issue. So it ran the simulations, but I think it did not combine the results for the those from the parallel jobs. Because I just went and opened the parallel job. This is W1. And when we go down there, okay, so I see there are doses. There are masses, but there are doses recorded for each of these zones with their uncertainty. This is the dose per incident particle, and this is the energy positive per incident particle. So this is basically the dose multiplied by the mass in kilograms. But it seems it did not combine these results. So let's see if we can fix that. And we can go to the main input. And now I can change the run option into, so we can, let's select analyze parallel jobs. Because I rarely honestly do this. I only use, so we can close and so let's save it. We need to save the file and then execute. Done. Then finished. So these are the parallel ones. And let's see if we got something to combine the results. Okay, I don't know why, but I don't see. So I'm not sure what's going on here. But I can see there is those for the parallel files. I can see that. If we go to W2, again, you see those recorded in those total. So I'm really not sure why it's not combining, or why it's not combining the parallel files. I don't know why. Okay. Any questions? Okay. The last thing that I want to show you is now how to use these latches in these exercises. Those exercises. I believe there are examples. Okay. So they have, this is actually an example of an input file where we are using a phase space file as an input. And this is another example, those XYZ in water, where we're using a beam source. So in order to get a beam source, those XYZ, we have to, this you can only compile it from the command line. So we need to go into the directory where the linac is. Okay. And then we type make library. Okay. Then we can use the linac as a library source. And we cannot do this from the graphical user interface. We'll go back to the those XYZ folder and let's copy the example where we're using Phantom and using space file. Okay. Those XYZ. This is those XYZ graphic user interface. Let's load this file, the example file, and we're going to use enhance. I'm not sure if they're using 5 to 1 or 700. It doesn't matter. We're going to select and we will look at the file information there. So if I go to the Phantom and look at the medium, okay, so they're using also the 700 SRE data. So I'm going to change that. Let's look at the source. The source is a full face space. This is source 2, and they are getting the face space file from the home directory. This is what we have actually run and combined. So the face space file has around 230,000 particles. So let's look at the latching. Can we do latching here? Okay. I thought we could do latching here, but I know for, okay, let's look at here. Okay. So maybe it's not, maybe we cannot do those XYZ. Those are Z for sure we can do. But I'm not sure, I cannot see latching every batch, space file. Okay. Okay. I cannot see that option here. So I might be wrong in that. But let's try the those are the those are the okay, this is those template. I'm going to use that. Not a big deal, but I need to go and change actually now the source. So we're going to change the source and let's change this face space file. I'm not sure which one is the face space file. We have to look into the manual then. 21, the face space file data. But let's look at if we can do the latching. That might be also, there might be a problem. Latches. Because I remember I used to do that, but maybe I'm wrong. Maybe it can only do within the latches. You know, Singh, I don't see it. Okay, I thought you could do it with the user codes because Andrew has it. Andrew has it with the, that's why he has that. Let's try it again. Okay, let's go back to those XYZ. I know it's MFCPP, he has the action. I've seen it several times. This is going to be 700. So particle source time. So this is 2. Okay. So here, phase-space beam input with no latch. So now we're going to do this. Phase-space beam input plus those components, which last with latch filter. And then the latch bit, now we have the inclusive exclusive. Okay, now we have it. Okay. So then we're going to put 10. Okay. And we can put 11. Let's see now. And we can run now the simulation. And let's save it and run it. You see the problem that is happening now? Because what's happening, it it wants to simulate 100,000 particles as I instructed. It's going through the phase-space file, particle by particle, and it's only going to use the particles that have a latch of 10 or 11. And since there are not a lot of particles, then it runs out. And then, okay, I ran all through all of these 200,000 particles in the phase-space file. I only grabbed 10. So I need to now repeat and use those 10 again and again and again. And that's why we're getting used all particles from source file, starting from first particle in line. Okay, so this is the reason why this is happening. But at the end, we will get the dose only from those particles that had latch 10 and latch 11 on. And you will get the dose per incident part. You can run the simulation again without the latches. I'm not sure. I think you cannot get the dose from the latches from the old particles. So probably you need to run the simulation again without latches. That gives you the total dose per incident particles. And then run it again with a certain latch that you're interested in. That gives you the dose per incident particle. And then you can actually determine the component or the fraction or whatever you're interested in. Okay?
Okay.
So it's there. You just, when you select the phase-space files, and maybe when you select source files, source probably you can also use latches as long as the latches are defined in the input file. Okay, because now when you use phase-space file, your latches are defined in the phase-space file. You don't care how did the the input file, how does it look like. But now if you want to use the linac library as a source library, then you just have to make sure the latches corresponds to what's in the input file. So okay, the job has finished, and then we can extract the dose, get the dose at a certain location, and that's it. Okay, so the dose in this simulation are only from particles that have latches satisfying the conditions that we set. Okay.
Okay. Yeah.
It's a particle. Yeah, this here. So we can inclusive, inclusive, inclusive for regions. So you just have to read more. Maybe uh, you can even specify things even more. It depends on what you want to study. But this is the general way of how we use latches to record cases. Okay, are there any other questions? There is another
Yeah,
linac.
I have.
Okay, go ahead.
Yeah. I want to know that if we just calculate the contribution, can we extrapolate to the multiple times? Like if we simulate thousands, like 100,000 particle, and
Okay.
then the contribution, what is the contribution from the JOS at the Dmax? So can we extrapolate it to 10, 100,000? Just multiply the number, or because it is
No,
different
sing,
ratio.
sing, sing. The doses are reported per incident particle. Okay. So what
Okay.
will happen is you have a value that, let's say, at for 1 million simulation. Okay.
Okay.
Now you want to, if you run the simulation 100 million, still you're going to get roughly the same dose per incident particle, but the uncertainty is going to be smaller.
Okay.
Okay. So the dose recorded is per incident particle. It's not a dose. Okay, it's dose per incident particle. It's not dose. Okay, because the dose is going to suppose you did a simulation. Okay, and I did a simulation with the same input file. Okay, you used 100,000 and I used 1 million. We should get the same dose per incident particle, but my results will be have a smaller uncertainty because I use more particles to simulate than you. So when I say, the same, we're talking about roughly the same with statistical uncertainty. It does not mix because this is how then we can actually talk together. Oh, let me tell you, okay, the dose I got is this per incident part. But if I told you the dose I got was 2 grays, uh, you need to ask another question. Okay, how many particles did you use? And so the doses are always recorded per instant part.
Okay.
Okay, keep that in mind. Keep that in mind. Okay, any other questions? So Bilal, there was someone who's asking something on Windows, the XView. Let's open it's a long email or long comment, and let me open the classroom. And I'm not sure if they have tried it and did not work or they have not. Okay, because it's the time. What is the command combine? Okay, I hope now, Sarin, you've seen how I'm doing this. Okay, so live, add space file, live, and so on. Okay, so this is exactly the command that I'm using. Okay, so in your case, probably the input file is whatever input file, and just use the same name for the output file. This is the number of parallel processing you've used. I start is going to be 1, unless you want to eliminate. Let's say you don't want to combine the first 1 or 2. phase space files. I-score is you probably have one phase space file, so this is also going to be one. Okay. Okay, here, Bilal. Thanks, Dr. Ramid, for all the input so far. I requested some time ago about how to run those XYZ show on Windows. Dr. Bilal, it's Dr. Windows, kindly assist. I don't know if those XYZ runs on Windows or not. I believe it does, because Sync has tried it, I think. You use Windows, right, Sync? But I don't know if Bilal has an issue, it doesn't run or it does run.
Sir, I have a question.
Okay, go ahead.
Sir, what is the advantage of adding two phase space file? Do we get
Okay,
more particles as output
no,
or something else?
no, okay. What's the machine you're doing simulations on? Do you run simulations or you don't run simulations?
Yes, sir. I run simulations
Okay, on Windows or on a Linux machine?
on a Linux machine, sir. Ubuntu.
Ubuntu. Do you do parallel
Yes, sir.
processing?
No, sir.
Okay. So basically what you're doing is you're submitting a single job. It's running on a single core. Okay.
Yes, sir.
Now, an advantage is if you have multi-core on your computer, you can split the job. So suppose I want, like what I've done now, I wanted to simulate 1 million particles. Okay.
Yes, sir. Yes.
If I simulate it on one core, on one machine, then
Yes.
suppose it's going to take 2 hours
Yeah.
to finish. But
Yeah.
now I can actually split the job. So I can split it. I have 8 cores. I can split it into 8. So each core can do, for example, 125,000 particles.
Yeah.
Not a million, but
Yeah.
125,000. But the total of the sum is going to be 1 million, right?
Yeah.
So on each core, I get a different phase space file, and I'm getting
Okay.
the results in 10 minutes instead of 2 hours.
Okay, sir. Okay, that is the
Okay,
advantage of adding.
that's the advantage of doing parallel processing.
Okay.
Okay, so then you
Okay.
combine them, then you use the. So always, if you have Linux, take advantage of running the simulations with parallel processing. So that is, you're going to get your results faster. Okay, you have
Yes,
multiple
sir.
core. Of course, Sync
Yes.
beats me.
Sir, I have one more question.
He has a 24 core machine. So imagine. Okay, go ahead. Yes.
Yeah, sir. Actually, in the IAEA phase space file website, they
Yes.
have. Actually, I was looking for a Electra precise machine.
Okay.
So I got the phase space file which are scored at the level above the JAWS.
Okay.
So, sir, is it possible to use that phase space file to get a PDD on a phantom at a isocenter level,
Yes,
100
it's possible.
centimeter?
It's possible. But what you need to do first, okay, you
Yes,
need
sir.
to, if you have from the company, you have the drawings of the linac, you need to now build an accelerator, but
Yeah.
the source is going to be that phase space file. And then
Okay.
you have the jaws below it, you have MLCs.
Yeah.
Electra, you have, I think, a pair of jaws, and then you have the MLCs.
Yeah.
And then you have, your slab or whatever. So it is
Yeah.
possible, okay? But
Okay.
my suggestion is you still need to, I have, for example, I have the same case for a two-beam machine with variant,
Yeah.
okay?
Yeah.
So
Yeah.
with variant, I get a phase space file above the jaws.
Yes, sir.
So in my beam, what I'm doing, I'm using the phase space file as a source.
Yeah.
And then the beam model itself has only the jaws, the MLCs, the exit.
Okay, sir.
So you need to do that. You need to get from the manufacturer these specifications, and then build your linac, but you can use the phase space file as a source. Once you have done that, then you can get it, you can do simulations, get PDDs or whatever you want.
Yes, sir. If sir, if the phase space file are given at 100 centimeter directly, then we can use it directly.
Yeah, but then they should tell you this is for a 10 by 10 field.
Okay, sir.
Okay, they have to specify what's the field size.
Okay, sir.
Otherwise, right?
Sir, one more thing. If the phase space file is for 30 by 30 field size, can you use it to generate a PDD for a field size of 5 by 5 centimeter square?
Okay, say that again. The phase space file is what?
If the phase space file is generated for a 30 by 30 field size,
Okay,
can we
so they
generate?
have, so the field size, the 30 by 30, and it is scored at 100, right?
Yes, sir.
Okay,
So we can use that. No, can we use that phase space file to generate a PDD for a field size of 5 by 5 at 100?
so what do you think? Is that accurate?
I think, sir, using those beam shaping X ZOR, size Y ZOR, I can. So is it possible?
So you basically want to, so basically the particles that are outside of the, outside of, let's say, more than 5 by 5,
Yeah.
you're not taking them. So you're only taking the particles within a certain region.
Okay, sir.
But my question, does that seem to you, does that look accurate?
Uh, I don't know, sir. Yeah.
I
It
don't
may
think,
not be
I don't
accurate.
think it's accurate. I don't
Yes,
think
sir,
it's
it may not be.
accurate. Okay. My suggestion is use that phase space file that is above the jaws. Get
Yes, sir.
information about your linac, about the jaws thickness, materials. Vendors are not going to give you exactly everything correct. Try to get
Yes.
something estimate, estimated thickness. If you want to play around, I would suggest just use two jaw pairs and
Yes, sir.
just set them to the openings of let's say 5 or 10.
Yes, sir.
So I think that is more for me. That is better than trying to take a face space file for a 30 by 30 and try to only call it to use region inside let's say a certain 5 by 5.
Yes,
So
sir.
for me that is better. Okay.
Yes, sir. Thank you, sir.
Okay. 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 So Bilal, is this okay? Those XYZ, does it work on Windows or it does not? Or does anyone know if it works or not? Okay. Please, it's possible to share from one or two of your published works how you can able to solve some problems using EGSnrc. You will find a lot of applications. Okay. Like I have one publication. If you go to from Medphys, don't know if you have access to Medphys, but I did something on surface doses. Okay, just trying to see if how accurately EGS predicts surface doses from a 6 and 18. So that was one publication. I had another publication on content current. I had to modify one of the codes. But you will find a lot. Okay. Uh, Dave Rogers, if you're looking for research frontiers in Monte Carlo, Dave Rogers, you have Jan Sundins, those are Frank Verhagen. I've worked with all three, and but there are definitely others. Those three, they use, I think, EGS a lot, but there might be others too. But I wish to appeal Dr. Rahman to assist with EGS++. Rahman is not with us. So there is an advantage actually, because then you can have more sophisticated geometries than what's available with the beam and those X, Y, Z, and those other. Although you can actually make these sophisticated geometries with Morphan, but X++ is a very easy way to solve this. Okay, so are there any other questions? Should we focus again back on AGS or ask Dr. Andrew to come back and help? Because he's helping me a lot with the MMCP, trying to get it running code. Because if there is not, okay, go ahead.
Dr. Nguyen, I have a question.
Yeah.
Yeah, for the second, I'm the one that pasted the suggestion on the classroom. For the second item I wrote there about sharing one or two, maybe in our next class, one of the publication, you can just go through it with us so that we can better see how we're able to solve the problem using EGS.
Okay. Okay, let me get something. Let's see if I have. Let's see if I have papers here. Okay, I thought I have it. Okay, let me grab it. I know convert it. Just give me.
I have a question, sir.
Yeah, go ahead.
I asked for putting and p-link the other time. I've not been able to get the file for
Which file?
MMCTP. Putting and p-link for connecting SSH. You say you will send the link. I've not been able to get it for Windows-based installation for MMCTP.
MMCTP. It's you're doing it with Windows installation.
Yes, I
think
did Windows.
Andrew now has it actually. Has actually links to these two files that are required.
Okay.
Okay, if you go to the GitHub, you should be able to find it.
Okay. All right. Thank you, sir.
Okay. Okay, I'm going to open this paper now. I'm not sure which one. Yes. Okay. So you reminded me of some work done some time ago, 2000. Okay, this is, for example, one of publications that are related to Monte Carlo. So we're measuring. It's a very simple project. We're measuring surface doses. We're using an extrapolation chamber that people believe this is the gold standard, the reference, and we're comparing the surface doses that are calculated with those RZ or those XYZ from a linear array. Okay. So one thing we had to distinguish, make it clear that with the chamber, you measure actually a percentage depth ionization. It's not a percentage depth dose. And with Monte Carlo, what we simulate is a percentage depth dose. So to convert percentage depth ionizations to percentage depth doses, there is this fancy formula, correction factors. The important part is the stopping power. But it turns out for photon beams that, as we go beyond Dmax and beyond, this stopping power, these factors and these factors do not change much. And that's why it's very safely we can say, look, the depth ionization is equal to the depth dose. And this is how we assume, when we tweak our beams, we look at PDDs and so on. But when we looked at the buildup region, this curve is a percentage depth ionization measured with an IC10 chamber. This is another percentage depth ionization measured with a roost. You see, beyond Dmax for 6, they all match. You have no problem. And this curve is the Monte Carlo curve. So the question is, why is this not matching these two? Okay. Well, people, and here we have it for 18 and B. Again, we see the differences between the three curves. This is for 6, and this is for 18. So the question is why there is deviation here, although everything matches beyond Dmax. So obviously, the first question is, okay, these are not gold standard. These chambers are not really reliable in measurements in the buildup region. You need to get an extrapolation chamber. Okay. And we do actually have an extrapolation chamber in our department. Okay. I'm not sure if there is a photo of it here or not, but with the extrapolation chamber, when we measured the PDDs with the extrapolation chambers, then we were getting, okay, this is the PDI. PEC is the phantom embedded extrapolation chamber. And this is the Monte Carlo. Still, there is a small difference, okay, between the two. But with 18, the difference is larger between the two. So the question is, because we believe, or people think that the PEC, the extravagant chamber, is the gold standard. Of course, Dave Rogers, Ivan Kwarkov, and the guys who wrote Monte Carlo, they said, no, Monte Carlo is the correct. You have something wrong in the measurement. This was the debate. Okay, the paper was all about this debate. Okay, so and here are some of these are in terms of values at 1 centimeter. What is our measured percentage depth ionization? This with the Roos chamber, and this is the calculated percentage depth dose for 6 with at 4 millimeters. See, 41 versus 48 or 49. Here at 18 is 23 versus 30. Okay. Now with the phantom, okay, we have because we could measure with the phantom embedded extraction chamber up to 50 micrometers. Here we're getting 17.5 versus 12.8. And then we have 15.5 for 18 versus 9.6. So you might say, okay, not much, but in terms of difference in the region, so this is more like a 50% difference. But when we take it back to Dmax, and this is what we often do, is this is about a 5% difference. But still, it's a difference. So one of the questions we had is, okay, maybe we cannot see the question I showed you at the beginning there. Maybe the stopping power in the buildup region actually changed with depth. So we need to probably, we cannot assume that this ratio remains constant. So we use the code SPRRZ to calculate the stopping power ratios. Okay, so these are the stopping power ratios, and these are relative. So we just divide it by that at Dmax. And so it gives me, this is the correction factor that I should use to my measurements to get the dose. But this is a 1%. Look at this difference. The difference is, let's say for 6, here, this is about 50% difference. 12 versus 18. Okay, 50%. So the correction factor is going to just account for 1%, not much. So this cannot explain the point we wanted to make clear to those who are writing the Monte Carlo code that, okay, this stopping power is not, cannot clear the, so because they're saying we have something wrong in our measurements. Okay, we did the measurements accurately as possible, but there might be, we admit there might be correction factors that we need to apply. The stopping power cannot cannot explain this difference. Again, for 18, I'm seeing even the stopping power is going the other way. It's a 5% difference, but cannot contribute to a 50% difference. Okay. So I hope now it's clear what is the issue between the two groups. So we have used the extrapolation chamber method. Just if you want to know how it works, you set the chamber at a specific depth, and then with the extrapolation chamber, you can change the volume of the chamber. Okay, so we keep changing the volume, decreasing it, and try to extrapolate to zero volume, because then this perturbation, there are some physics behind it, and perturbations produced by the side scattering, lack of side scattering electrons, you eliminate those. So that's how extrapolation chamber works, and that's how people use it as a gold standard. This is a typical type of measurement. You set the chamber and then you decrease the volume, and we plot the values or PDDs as a function of decrease in volume, and we extrapolate that to zero volume. So here we were getting something around 16%. This is for 6 at 50 micrometers, and for 18, so we're getting something about 14%. Again, with Monte Carlo, this is not equal to Monte Carlo. Remember, it was lower. Okay, so let's go back. Yes, so this is with 6. This is what we were getting, about 50. The best we could do is get 16% versus 12 or 30. And for 18, this is about 14, 15% versus 9.5. These are the PDDs at 50 micrometers. This is measurement, and this is with Monte Carlo. Of course, this is PDI, or 0 water PDI. So the next step, we said, okay, maybe we're doing something wrong. We cannot compare ionization ratios to those ratios. We need to make sure that everything is fine with Monte Carlo. So what we have done is, in Monte Carlo, we actually simulated our chamber. This is how the extrapolation chamber looks like in the dose RZ geometry. And this is the gap, the separation. And what we did was forget about the other correction factors. At least the dose in the air should directly be correlated to the ionization that we'll measure. There is no correction factors, no stopping power. I don't need that. So we have modeled this chamber and placed this chamber with 0 centimeter and with, let's say, 1.5 or 3.5, mimicking exactly the experiment that we did. So the ratio of the doses from Monte Carlo from both should match the measurements if everything is fine. If there is a problem, okay, then that is open for debate. What's the issue? So this is, for example, now when we have simulated the ionization or in our chamber, and we're recording the dose in air, that's what we call PDI. We get an agreement in the 6 MV. You see there's agreement between what we have measured and with the Monte Carlo. So at least for 6, we can say, okay, we really don't know the correction factors. We have the calculated PDDs from Monte Carlo, and this ratio or difference, that is going to be our correction factor. So now we come to, terms together. We agree, both of us, that our measurements is correct. but we just don't know how to convert the measurement into those. We're measuring ionization, and with Monte Carlo, that it can help us to do this conversion. But when we looked at 18, with our method, it still did not work. So we're still seeing, although we're simulating the chamber, we're still seeing a difference between the simulated ionization or PDI from the chamber and what we are measuring. So this was really a problem for us. And in the paper, then we started to, okay, what is the issue? Why do we have, you see here, this is the calculate PDIs. Okay, there is an agreement. So the first thing we thought about, we tried to look at different things. What could, I mean, people could say, look, maybe your miler, maybe you're not at 50 micrometers, maybe you're at different level and so on. Although it's measured accurately, but with a miler, it had because we're using it as an electrode. So in the here, there is a very thin thickness of aluminum. Okay, and we did not know what's the thickness of that aluminum because it's an electrode. So we said, okay, let's assume that this 50 micrometers. We're going to assume first it's all miler. There is no aluminum layer in it. We're going to take another look at, okay, I'm going to divide into 25 miler, 25 aluminum, and then full aluminum. Okay, and this is what the manufacturer said. Okay, that miler foil, it's about 5 micrometer aluminum and 45 micrometer miler. So we did repeated simulations. Okay, and still that cannot explain the difference. For 6, no problem, but for 18, it cannot explain the difference. Okay, the guys cannot claim that, okay, maybe I don't know correctly the chamber, my chamber design accurately to explain, you know. What we've looked at again, we said, okay, maybe the cross sections, because at that time we were using Storm Israel photon cross sections, but XCOM was available, and our group, we were the first to actually. Well, I don't like to use the word first, but we actually included XCOM in EGSnrc. So I had to go get the XCOM data, figure out how it looked like, and then we tried to find a way so that the XCOM, the simulation runs with XCOM cross sections, not with the Storm Israel. Now, of course, it's just selection, you know, drop down menu. So the data we work together with the developers on EGSnrc so that they have this option available. So we moved, changed the cross section data. It's still, I'm not getting an explanation. Okay. We thought, okay, maybe there is, you know, when you do the modeling of the linac, okay, maybe there are some sources there in the head that were not taken into account. Maybe the shielding, okay, were not taken into account and so on. So, okay, we want to eliminate that. So what we have done in the simulation, let me go back and let's use so we're going to, this is an example, the linac that we've opened. So let's preview the linac. So imagine there is some shielding here. This shielding actually produces electrons that affect the measurement. So it will increase the surface dose. But since in Monte Carlo, this region of is not actually modeled, Okay, it does not increase the Monte Carlo, and that can explain the discrepancy. Okay, so what we have done, we said, okay, suppose that is correct. We going to place here solid water. We placed about 12 centimeters of solid water. And the reason is those hidden sources of electrons generated up there, they're going to stop in the solid water. But the solid water is going to be a source of contaminating electrons. But that is geometry-wise is well defined. Okay, so that's the idea behind what we have done. And let's continue. And again, when we did that, it still did not uh, we did not resolve this disagreement in the EGSnrc. So we cannot assume that there is a hidden source somewhere that my geometry in the Monte Carlo is not correct and so on. Okay. We've looked into, okay, there are neutrons with EGSnrc. That has, and with Monte Carlo, EGS does not model or simulate neutrons. So maybe I'm measuring the neutrons with the chamber. That's why I'm getting a higher dose than what's modeled by or predicted by Monte Carlo. So we use TLD 600 and 700, and yes, there is a small contribution, but it cannot be cannot explain, the difference. So this is the cross-section data. Okay, that's one. These are neutrons. And the last thing we have, okay, this is also another contribution from our side, is with Monte Carlo, EGS at that time, they did not simulate triplet production as a triplet production, but triplet was simulated as a pair. Meaning that when you have a photon undergoing triplet production, we only get the electron positron pair. But in a true triplet production, we should get the 3 particles. So the debate we had is, okay, maybe we're not getting enough particles with Monte Carlo that reach the surface dose in the simulations, and that's why the dose is going to be lower. So we made a very crude modification to the physics to model or to incorporate triplet production. Now, by the way, triplet production is fully simulated. Okay, they did not take the way we have modeled it because our way was very, very crude. Okay, but we wanted to show something that, but they actually have a better model, definitely. So what we have, what we saw is that, okay, this is the dose using our modified triplet compared to the dose without triplet. So there is about a 5% increase, let's say, in the surface, dose-wise, okay? Not in the PDD. So that's not a 5% in the PDD, that's a 5% increase in the dose. Remember, the dose difference is 50%, but in the PDD, that's about 5%. So this could get at most 1% closer to the PDD. It cannot explain, why we have this difference. So at the end, this was the whole thing about the paper. It's all about this debate between us and the guys at NRC. By the way, I was in Montreal, so they were an hour and a half away, and we had a very good relation with them, and so on. So at the end, we came up with the conclusion that, okay, there is something that we don't understand with EGSnrc, why it cannot make this prediction correct. It took them Ivan took him about, I think there is a publication 2 years later following our results, and they have found some bugs in the code. And they used our data that we have measured as a benchmark. Benchmark meaning that you develop something with Monte Carlo and you believe these experiments, they give you excellent data results. So a benchmark is you show your code, gives results that match those experimental data. So our data is used actually, was used as a benchmark for these modifications. So this is brief, how we use Monte Carlo. And I'm showing you that I've used the dose RZ, dose XYZ. I did not develop something really fancy, something very simple, just a measurement of a PDD. But there was a lot of work, involved in doing that. So this is an example of how we use Monte Carlo. This is my experience with Monte Carlo. Others, for example, they use Monte Carlo to calculate correction factors for and many more, topics. Okay. Okay. Are there any questions, or did we conclude today? So your question took me back 15 years back. This publication was, I think, 2004. Any other questions? خلاص بلال كده نقفل. Conclude, or you have something you want to add? Okay, in that case, then I'm going to conclude the session today. I'm going to see next week if Andrew is going to be back. But if you have things related to EGS, please post them on the classroom. I'll try my best to answer as much as possible. I might actually also try to do a small tutorial video just to show how you can run the example linac. By the way, just one second, because there is another linac, another demo. So let's look at it. Okay, quickly load the previous input. We're going to look at this other linac. It's the electron linac. So it's the 10 MeV electrons. Okay, I'm not sure what's the text data file. Yeah, okay, this is something that's not. Oh yeah, because I loaded it. Let's go and load again. Load this. Okay. This is a demo accelerator. I probably use the one. Okay, it's 5 to 1. So let's change the text data file. So for electrons, they use the 5 to 1. And now when I preview the accelerator, you see it.
Dr. Umu, we can't see your screen.
Okay, let me share. So I'm going to open it again. Open the electrons again. Okay, so it's the other linac. So you need to compile, and probably you need to get the input file again from the examples under the in-house directory. So I have everything here, and it's the EX10 MEV. Okay, And again, you have a primary collimator chamber. Obviously, you don't have a target. For electrons, you don't have a flattening filter. There are scattering foils. There should be, so constant, there should be scattering foils. And then you have here, so the scattering foils are probably, these are the scattering foils. You have the chamber, you have the mirror, um, and then we have jaws, and then we have the applicator. So this is how the applicator looks like. Again, you can run the simulation and get particles at 100 centimeter. So for example, probably you're going to find, if I'm not mistaken, maybe half of the particles in the space file are actually photons, although this is an electron beam. But their statistical weight might be very small, their energy might be very small, but we do have contaminating photons with electron beams. So I wish if one could run just 1 million simulations and can give us an estimate of the number of photons to electrons reaching, the phase space file. Yeah. But this is another example. You can play with it. You can change things, okay? But be careful, because sometimes, like in photons, when you change the energy, the model that we have there is for a 16 MV beam. If you decide to go for a 6, okay, probably the flattening filter is wrong. It does not represent the flattening filter for 6. The target is too thick. Okay, so be careful about you know. Don't take the results literally, because when you change the energy, you have to change some of these components. Again, for electrons, probably the same thing will matter for the scattering foils. The rest nothing should change, but the scattering foils, they are energy dependent. So be careful just about that. Okay, any other questions?
Thank you so much, Doctor. We are so grateful for the knowledge impacted so far. I want to make a request. I don't know how it will look like. I don't know if it is possible for us to have like a flow code of how to go through these processes. For some of us who are very, very new to this Monte Carlo simulation, I know you have been in this field for quite some time. Sometimes when you are typing the command, you believe that all of us we're on the same page. Before you even catch up with what you are typing, you've moved to the next thing. So I don't know if it is possible to just have a flow code. You want to run this simulation, you move to this one. If you are going to X-ray, so that we can be able to tie up all what we have been doing from the beginning of this class, and then we can be able to apply them appropriately. Mostly, I am more concerned about my PhD program for me to be able to apply all what I've been learning. But honestly, sometimes it looks somehow to be able to bring all of them together. When you are explaining it very straightforward, one is flowing with it, but to bring them together, okay, bring PEX file, PEX data file, bring the water file and some other things. I don't know if it is possible to have a flow code for us to be able to follow through the steps and the processor.
Okay, remember, first you have to determine what you want to do. Okay, that's number one step. Because then you can decide, I want to model a linac, I want to model an X-ray tube. Okay, but first you have to determine what exactly you want to do. The next step is we need, for all of these, all of the work that I'm doing, we need the geometry. Okay, we need to figure out. So the first approach is I go to the vendor. Okay, please, can you provide me with some geometry that can help me to do Monte Carlo? Some might be in the literature, some might not be in the literature. The vendors might give you things accurately or might give you something approximate. But get the geometry, get the materials. Okay. Once you have the materials,
okay,
now I have all the data that I need to start to do Monte Carlo. So the first step will be, okay, I need to build, for example, a based on the model that the manufacturer gave me, okay, and the materials. But the materials, I need the cross sections for the materials. Then I need to do that with a fixed. So I need to prepare a fixed data file for the materials. Okay, so you have to take it one step at a time.
Okay.
The first linac I have modeled, actually it was not a linac, it was a cobalt machine.
Okay.
Okay, and it
Okay.
took me a while. It took me a while, and I did not have a graphical user interface. I had to do it with, the text editor. Okay, edit the input file with the text editor. It took me a while. Be patient, but once you know this flow, then when you practice it, you will become more efficient. Then you will know where I need to go to modify this, to do that, and so on. So the point now that you need to do is, okay, I want to run. I mean, if you can practice just to run this demo simulation, then we are on the first step. Then you can come up with something on your own. I want to do something different. Okay, then you need to know how to build your component modules for the linac, the geometry, and you take it from there. Okay, so be patient. That's my advice.
Okay, sir. Thank you so much, sir.
Okay.
Thank you.
Okay. Okay. So any no last questions? Okay, then in that case, then thank you very much. This will be in the, probably by tomorrow on YouTube. I'm planning to actually just do some small videos, some small demos, like run a linear simulation, run this, especially the demo files, how to run a those XYZ, because I actually have the text data, how you do that. But maybe like what Noah said, I need to tie things up with maybe a linac and simulation. So I'm thinking of doing that. Please. Okay.
When is that? When is that, sir?
I'm gonna when I have time, I will start to do these small videos. Okay, like how to run those XYZ. I'm not going to explain every detail. I cannot do that. That's going to take a lot of time.
It's just simple notes.
Simple, but probably just simple. Okay, this is an example file that you should find in your installation. This is how you're going to run it. Okay, and this is how you check the data. This is the data you can find it here.
Okay, sir.
Okay.
That will be fine, sir. Thank you, sir.
Okay. Okay, in that case, then we'll conclude now, and good night to everyone, and see you. We'll see you next week if Andrew is going to be back. But please post your request in the classroom. Okay, good night.